So this is going to be a bit of an overview from my PhD, which was funded by Research Ireland and Boston Scientific, and then how that's led into my postdoc project, which is funded by Amber, again in partnership with Boston Scientific. So aortic stenosis is a disease of the aortic valve that leads to inefficient blood flow to the rest of the body, and it carries 50% chance of mortality within 2 years if it's left untreated. Thankfully, there are treatment options for this disease, which are valve implantation techniques. However, the devices that are used for this application either require the need of lifelong anti-coagulant therapy, which is very limiting for the patients, or the materials suffer from premature failure, requiring patients to need reintervention surgery later on in their lives. So due to the pitfalls of these two devices, there has been a current drive in the development of polymer heart valves. Polymers give us the availability of tunable mechanical properties and structure, which can enable us to draw inspiration from the native leaflet structure. And this could allow us to create long-lasting devices that remove the need for anticoagulant therapy. Now, at the moment, there are a handful of polymer devices in development, ranging from surgical valves that are currently in clinical trials to bio-inspired devices and even into the tissue engineering space. And what this has shown is that this has shown the feasibility of this technology for this application. However, there's such a wide range of materials that we can look at and structures that we can design. We need a directed approach for the design and development of these devices. So that leads me to the aim of my PhD, which was to create an finite element-based framework for the design and optimization of 3D printed polymer leaflets. This framework has 3 primary areas of focus. The first is the development of a tri-leaflet valve model, then using this to determine the key structural features within these leaflets, and then finally using it to optimize the fiber orientations within the leaflets. Ultimately, this delivers upon a novel polymeric heart valve device. So I'll go through each of these briefly. So starting with the tri-leaflet valve model, the first step in this was to understand the native tissue that it is we're trying to replicate. So I performed mechanical testing and imaging of native porcine aortic heart valve leaflets to give me mechanical properties of these leaflets, as well as understand the dominant fiber orientations. And the next step was to identify an additive manufacturing approach that we can use to recreate these leaflets, and identified multi-lecture writing, or MU, as an ideal additive manufacturing technique, as it's a highly controllable extrusion-based additive manufacturing that enables us to create fibers at a biologically relevant scale. And through printing these fibers, we can then embed them in elastomeric silicone materials, and we can create these fiber-reinforced leaflets. And then taking this one step further, we can use FE tools to model these composite materials and understand the mechanical response of them. And then we can describe this mechanical response using constitutive models, which enables us to reduce the complexity of the FE models. So now we also have a fiber reinforced constitutive model. So taking all of these learnings, I then applied them to the Boston Scientific Accurate Neo2 heart valve device as we were working with this company. Here you can see an image of the porcine pericardium leaflets in their valve. I created a model of these leaflets, partitioned it into 56 discrete regions, and then using my imaging that I performed earlier on the native leaflets, I was able to define local fiber orientations across the leaflet. Here you can see an image of what that would look like if it was printed, and you can see the fiber pattern swooping across the leaflet. So then repeating this 3 times, I was able to then create this tri-leaflet valve model. In this model then, I could dynamically apply pressure from both the top and the bottom, so we could open and close the valve like it would during the cardiac cycle. And this enabled me to look at material response of the leaflets, as well as clinically relevant metrics of valve performance. So here you can see a video of what that valve model looks like with the bio-inspired fibers. We can see it opening and closing, and we can also see the strain on the leaflets across the cycle. But the benefit of this model is it enables us to look at a wide variety of structures. So here you can see 5 different reinforcement structures going from bio-inspired, circumferential, radial, highly dispersed, and then just silicone. And what you can clearly see is the dependence of the leaflet response on this fiber reinforcement structure. So we see that we have very high strains in the leaflets in the 3 models on the right, and then you can also see how that impacts how the valve is opening. So what we saw from this work was that poor fiber reinforcement leads to worse material outcomes and valve performance. So now that I've created this model to enable me to look at different valve structures, I can then use it to help me determine the best structural combination for these leaflets. So the main question that I wanted to answer here is, what is the best combination of mu and silicone to enhance valve performance? I looked at 3 key features, so the number of layers, the fiber spacing or pore size, and the overall thickness of the silicone into which the structure was embedded. And I used a DOE or design of experiments approach to map out the minimum number of combinations of these features to enable me to see the impact of each of them and ultimately obtain the optimal combination. So again, I use my FE methods to extract the stress strain response for all of these combinations, and I could then input these into the valve models. And I evaluated these by looking at these clinically relevant metrics for opening and closing, as well as material stress and strain. So using this methodology, I was able to determine the best combination of structural features for 3 different thickness leaflets. And here you can see a lot of plots, but this is basically highlighting that I was able to compare them by looking at the leaflet stress, strain, how much it opened and closed. And through this, I was able to determine the best combination for this particular application, which was a 0.3 millimeter thickness leaflet with 2 layers of mu and then fiber spacing of 0.5 millimeters. So using this, I've been able to obtain the best combination of these structural features. So now moving forward, what I was able to do then was further optimize the fiber orientations within these leaflets. So coming back to the native leaflets, you can see here images of the leaflet on your screen, or on the screen, and you can see that it clearly has these specialized fiber orientations across the leaflet. And I used this to help me create this bio-inspired valve design, which we can see gave a very effective design. But there are quite a few differences between the native leaflets and this commercial leaflet. So the native leaflets have a very variable thickness across them. Meanwhile, the commercial leaflet is a uniform thickness, and also the shapes of the 2 different leaflets are slightly different. So this would lead us to think that the optimal reinforcement structure in our commercial leaflet may not be exactly the same as what we'd see in the native leaflet. So what I would like to do then is optimize the fiber reinforced design by orientating the fibers to minimize the overall strain in the material. So to do this, I implemented a fiber reorientation algorithm that reorientated the fibers in the material with respect to the directions of max and mid principal strain. And what this did is it looked at a model with fully isotropic fibers, and it looked at the directions and magnitude of max and mid principal strain. And then it reorientated the fibers into 2 families about the directions and magnitudes of this strain. And to do this, I simplified my model slightly. So I used a single leaflet with a static pressure applied, and then I flattened it afterwards to enable me to look at the fiber orientations. I also looked at 2 different methods of reorientation. So one reorientated the families symmetrically about the max principal strain direction at an angle that was related to the magnitude of mid to max principal strain. And then I also looked at a second method, which simply aligned the 2 families along the max and the mid principal strain directions. So here you can see what the leaflet looks like with just isotropic fiber orientations. And then we can see the results for the 2 methods of reorientation. And what we can clearly see is that by reorientating the fibers to be able to bear this strain a bit better, we have lower strain across our leaflet. But to really be able to understand how well this works compared to the bio-inspired model, I needed to then put these fiber orientations into that dynamic opening and closing valve model. So here you can see the original bio-inspired valve, and here we can see the results from the first method of fiber reorientation and the second method of fiber reorientation. So if we pause these so we can look at them a bit better, we can again see that there is a reduction in strain in the reorientated models versus the original bio-inspired model. And our valve is still fully opening and fully closing. So what this has shown us is that optimization of the fiber orientation successfully reduced the overall leaflet strain while maintaining valve function. So through this, I've been able to develop this 3-step FE-based framework to enable me to design and create these novel polymeric heart valve devices. So moving forward, the aim for this is to integrate this into a singular polymer leaflet design toolbox that can be embedded in the company that we're working with. So engineers can look at the materials of interest and also desired leaflet responses, use this toolbox, and be able to define their optimal leaflet combinations. And taking this one step further, we can actually then manufacture these materials, and we can suture them onto frames and be able to actually test the valves and how well they work. So ultimately, this toolbox can be used in the company to enable us to design leaflets and valves for lots of different patient-specific applications and different frame designs, ultimately enabling us to design the future polymeric valves for the treatment of aortic stenosis. So thank you all very much for your time. Thank you to my group.